Hello. Today I'm going to talk about how to run Xen without a direct map, and this is part of the project of building a secret-free hypervisor. And my name is Hongyan, and I'm from AWS. So, why do we want to build a secret-free hypervisor? The problem is that we have seen all these speculation vulnerabilities, and they are definitely not the last of them. So we're probably expecting more, which are probably on their way. So those hardware bugs and speculation, they break the isolation boundaries. In the last year's Xen Summit, we rethink the design of Xen. So can we just not expose those secrets in the first place? Can we just, if we want to access some part of secret memory, we map and unmap those memory on demand. So we don't just permanently map them all the time. So this is the idea of the Xen Summit last year. So we want to build a secret-free hypervisor, which has two major components. The first one is to remove the direct map. So this is going to be covered in this talk. And so far, it's more or less done, and it's being upstreamed, and the patches have been posted upstream, and it's under review. And the second component is per-CPU stacks. This is future work and is not covered in this talk. Okay, so we want to remove the direct map, but why do we want to do that? The reason is that just like Linux and a lot of operating system kernels, so Xen also has a permanently mapped window to all physical memory, and it's a one-to-one mapping. This is not entirely accurate because it's not necessarily one-to-one. It does not cover the entire physical RAM, but I will explain those details later. And basically, having access to this window means having access to nearly all memory. So we have this window just because it's convenient. And because the direct map window is always there, we can just always use that to access memory. We don't need to map pages on demand. So this is also good for performance. But it also means it's really convenient for attackers to use this window to access probably the entire physical memory. So we want to block those vulnerabilities. That means we also want to block access to the direct map window, which means we want to remove it. Okay, so this is basically a diagram from 2019, the Xen Summit. As you can see, this is building a secret-free hypervisor is definitely not that trivial. It has a lot of dependencies, and of course, there are cross-dependencies between two major components. One is direct map removal and a per-CPU stack. On the right-hand side is not going to be covered in this talk. So in this talk, I'm going to share my progress on the left-hand side. So let's remove the per-CPU stack out of the picture. So to remove this direct map, as we can see, we still have a lot of dependencies to be completed. And I will talk about each dependency very soon. But to give you a basic idea of how many lines of changes are required, you can see some of the dependencies are very easy. Some of them are they're not difficult, but they require a lot of rewrite and changes in a lot of the source code. And even if you meet all those dependencies, there are still some bugs around Xen which require another 700 lines of changes to actually eventually remove the direct map. Okay, so I'll just break down all those dependencies one after one. The first one is we want to move Xen page tables to DOM heap. So why do we want to do that? The thing is that currently Xen page tables, they are on the Xen heap, and the Xen heap is permanently mapped, and it relies on the direct map. So in order to make Xen function without direct map, Xen page tables themselves, they cannot rely on the direct map. So that's easy, right? We just move Xen heap we just move Xen page table to DOM heap. It turns out that we need to rewrite a lot of code in the Xen source to move each call site to DOM heap, and we need to rewrite all the call sites. And I'm really grateful to Wei because he's written most of the code, so I could just borrow most of the code from him. And basically, we now have a new API to allocate and free Xen page tables. And they are based on MFN instead of the direct map address, which means that you need to allocate and you need to free. And also, when you want to access those pages, you have to also call map on map explicitly instead of just using the direct map window to access the memory. The next item is in the last year's Xen Summit proposal, because the direct map window is gone, we still need to have a Xen keep somehow. And naturally, the choice is to implement Xen keep pages on VMap because VMap is also globally mapped. Naturally, that becomes a choice for us. But when I try to implement this idea, there are quite a lot of problems. The significant problem is that now the virtual address to physical address, or vice versa, the conversion API is now completely broken. So, and even if let's say we try to make it work, now the VA to PA conversion, we have to walk the page tables. It's no longer fast. And PA to VA, it's very difficult. We can probably try to add a new field in the page frame table, a page info structure. Or we could try to see if there are any fields in the union we could just reuse. But it's definitely not going to be trivial. And even if you solve all these problems, still there are a bunch of call sites which actually partially unmap a Xen keep allocation. So you can allocate a big Xen keep region, and then you just free part of it. And unfortunately, VMap in its current state cannot support this very well. Okay, so what I did basically, because removing the direct map, at least at the moment, it still means the direct map address range is still there. So why don't we just reuse that address range? So my implementation is when you allocate a Xen keep page, you map into that region on demand. And when you free the Xen keep page, you just clear the mapping, which basically means all those things are still working, like the macros, the conversion macros are still working. And it naturally just supports partial unmap of Xen keep pages. So that's the biggest change I've made compared with the proposal from last year. Okay, so now, of course, another dependency, which is we need to invent a new mapping infrastructure in early boot for bootstrapping, because now the direct map window is gone. We need to have some structure to actually bootstrap other mapping infrastructure. Okay, so we need to add a PMap, which is basically reusing some fixed map entries for early boot, which bootstraps the map cache for the idle domain, which then bootstraps other map caches for like DOM0 or DOM-U. Okay, dependencies are done. So the final step should be very easy, right? Now all those dependencies are completed. We could just now flip the switch and say, now there is no longer a direct map. Unfortunately, as we all know, Xen can be slightly broken at times. So the code, after you switch off the direct map, all those bugs that were hidden before, now they start to emerge. For example, there are code which accesses the DOM key pages via the direct map. And even if you access the DOM key pages via direct map, like I said earlier, the thing is that the direct map does not necessarily cover the entire physical memory. So especially for PV, because PV, the address map of PV address map, it only covers part of the direct map. So it could very well be that when you try to use direct map window, it simply will crash, or you will have some strange bugs. And of course, we used to use a direct map. So if you forget to unmap something, and if you map something twice, they won't show up, because with a direct map, those things used to be just knobs. But now without a direct map, we have to fix those bugs. And of course, the map cache only exists for PV. But now we have to create the mapping infrastructure. We have to initialize the map cache for the idle domain and for HVM guests as well. And there are some other bugs, which means we need another 18 patches to fix Xen, to make it work without a direct map. I will give you a quick example of sometimes Xen is broken. So basically, if you look at the code on the right-hand side, so we allocate something on a DOM heap, and we immediately forget that those are DOM heap pages, and we start treating it just like Xen heap pages. So we just use direct map macros, and then we access those pages on direct map. The thing is that this code is not even some obscure code. This is PV DOM0 creation. So I basically have to rewrite how pages are accessed in PV DOM0 creation. And of course, there are a lot of other bugs like this. And those bugs, they just won't show up when you have a direct map. OK, so after fixing Xen to work with no direct map, of course, I'm not claiming I fixed them entirely. We can finally answer the question that was left unanswered last year. So what is the performance? What will the performance look like when we run Xen without direct map? OK, so for now, I haven't done a lot of comprehensive benchmarks, but mostly I've done HVM benchmarks. So the good news is that for single-threaded benchmarks, mostly CPU-heavy benchmarks, they are basically unaffected. But when you go to multi-threaded benchmarks, I can see a consistent 2 to 5% performance drop. And the really bad news is that for MMIO emulation, this is all for HVM guests, by the way. So for MMIO emulation and HyperCall micro benchmarks, I can see a latency increase of 40 to 60%. OK, so we definitely need to address these problems. And what are the root causes, and how can we optimize? So the first problem is due to map cache and how map cache is currently implemented. So without a direct map, we have to use the map cache to map unmapped pages on demand. The thing is, the existing map cache implementation has a per domain lock. So each vCPU has its own cache. But the thing is, if you miss in that cache, that vCPU has to go to the per domain area to fill some entries, to change some entries, and probably also fill the vCPU cache. The thing is that that region is protected by a per domain lock. So as you can imagine, when the vCPU count is really high, eventually this will become a bottleneck. And you can see that you can consider, especially in multi-threaded benchmarks, you will see a consistent performance drop. And naturally, the idea is to rewrite the whole infrastructure into a purely per vCPU structure. So now I've basically rewritten the structure. So each vCPU has its own cache and its own area, map area. So there are no locks, and no vCPUs need to share any state. Especially for map and unmap, they can completely function on their own. So there are no lock contentions. As you can see, with the new structure, with the new per vCPU structure, we can basically see the multi-threaded benchmarks. The performance is improved quite a lot, and they almost match the performance when you have a direct map. OK, so what about the next one? So why do MMIO emulation and HVM HyperCall, why is latency increased by so much? Of course, the trouble is page table walks. So whenever you do a MMIO emulation and when you do HVM HyperCall, the argument is passing using the guest virtual address. In the worst case, it means we have to do a 2-level page table walk, which in the worst case can cost you 20 page table walks, which of course, if you miss all the time in the map cache, it means 20 maps on our maps. This is actually really, really bad. 20 maps on our maps, in the worst case, if you miss all the time, it can cost you a lot of latency and extra mapping on mapping. So can we optimize this? Can we? The first idea came to mind is, can we just cache the translations? We can. We can probably cache guest virtual to MFN, but then we somehow need to monitor the guest and EPT changes to invalidate or to update the cache. Probably some shadowing page table shadowing is needed, or we can just cache the EPT, so that it means the guest physical address to MFN. That can also work, and because EPT is rarely changed, it means the cache does not need to be updated that often. So that can be effective, and that means that we can save all those EPT walks. So we only need to walk the guest side. So it means probably only 4 maps if you can hit the EPT cache entries. That's the solution is not trivial, and of course, recently on the mailing thread, there is the proposal of probably adding some hypercalls using the guest physical address. Actually, I'm really in favor of that idea, because that means the performance issue is going to be resolved. And of course, in the short term, that's not a solution, because that means guest operating system changes, and that will break the ABI. At least that's not a short-term solution. So can we think of other solutions to this problem? So like any responsible engineer, the solution to this problem is to deny the problem exists in the first place. So this project is called secret-free hypervisor. So we only need to hide secrets. What about EPT? Do they contain secrets? At least my conclusion is they simply don't contain secrets, because the guests don't even have control. I mean, precise control of EPT, and the guests cannot even store secrets in EPT. So do we really need to hide EPT entries? We probably don't need to. So just leave it on Xen heap. Now I will just move EPT entries to Xen heap. And remember in the previous slides, the Xen heap implementation is still in the direct map window, although it will in the direct map window, although it's now mapped on demand when you alloc and free all those. So it means, okay, that implementation means the VA to PA is still fast. It means the EPT walking, we basically now pay little cost in EPT walking. It's almost like what we used to have, just when we used to have the direct map window. Okay, so the benchmark shows that if you have a direct map, so basically I'm using the HPAT emulation micro benchmark to test latency. And if you have a direct map, that's 4,000 nanoseconds. And if you map the EPT, of course, you can see there's still 10% increase in latency. That's because you only map the EPT, but you still have to map the guest page tables. So you save the majority of the cost, but you still have to map some page tables. And if we leave everything unmapped, which basically means we have to map and unmap the guest page table and also EPT, that has a huge increase in MMR latency, like more than 60%, which will propagate to real-world workloads. And at least now, if we do it this way, we only have a 10% increase. Of course, it's still not ideal, but we at least avoid a huge performance drop in if we leave everything unmapped. Okay, so these are the 2 biggest issues that I found in benchmarking HVM guests. And after addressing, of course, address one issue and just completely deny the second issue even exists. After addressing the 2 issues, so we now reach the conclusion. So basically, at least in this implementation, it's certainly feasible to run Xen without a direct map. And it removes a major attack surface. And this can be done without breaking the ABI or API or huge performance degradation. So after addressing the issues, now for HVM, so the real world workloads, they are almost all within the 2% performance drop. Yeah, so that's the progress I have so far, and I'm really glad to be here and share my progress. Of course, I still have some questions for the community for discussion. The first question is probably just for myself. So so far, I haven't cared about PV guests. So mostly I've been benchmarking HVM. The performance look pretty acceptable within 2%. But what about PV guests? Even though I don't care about PV, upstream still does care. So I also need to benchmark the PV guests, which probably will also see some other performance drop because all those page table hypercalls you probably now need to map and unmap all the time, which is even worse than HVM, of course. The second question is, we just remove the direct map and we just keep Xen heap as is. Even if we use the VMAP to implement this, it's still globally mapped all the time. The next question is, what data structure on Xen heap need to be hidden? For example, like we now more or less, even in the proposal last year, we more or less ignore this problem. But I think that some data structure on Xen heap still need to be hidden. They cannot be mapped all the time. They can be considered secrets. So, for example, like shared info, or vCPU info, they are now Xen key pages. They are mapped all the time. But we probably need to think about whether we want to map and unmap them, and what are the extra costs of hiding them. And of course, the third question is, we definitely haven't reached this point, but let's say eventually we hide all the secrets we want to hide. Can this replace other mitigations like cache flushes, fences, or even KPTI? Of course, this does less than what KPTI does because this still exposes the Xen image and the other stuff. But if we hide all the secrets, probably we don't even really need to care about exposing the Xen image itself. Okay, these are my questions for community to discuss. And that's my contact detail. And I'm also on IRC if you want to reach me. Yeah, so we still have time left. Any questions? Thank you.
You actually have a lot of questions that have accumulated in the chat. I do actually have an answer for one of your questions, though, the performance of PV guests. So at the moment, because PV guests expose high mem low mem split in the direct map, and that 64-bit PV guests are preferentially allocated from the top of memory downwards, your chances are you're already mapping and unmapping for the page table operations that exist, because PV would be allocated high enough for you to already need that. The other aspect of PV guest is that so the do-mu update hypercall actually runs with recursive page tables, and that will not be affected by any of the changes here. So I don't expect you to see a massive difference for a PV guest because of these changes.
Okay, thank you. Although I do have a concern because so far, at least on my test platforms, the PV low mem and high mem split, I think it's around 5 terabytes. So I actually don't have any machine that exceeds that amount. So basically now what I'm seeing is that map on map is still in the low mem region. So still, at least on my test machine, they still use the direct map. But I mean, once direct map is gone, everything is high mem now. So I will just test it and see what the performance would be like.
So there is a debug command line option for artificially lowering the high mem boundary for testing that, but it has resulted in triple faults for at least 3 versions of Xen. If it would be helpful, I could see about trying to fix it.
Okay. it's possible that this series can probably already hit that problem and refix this. I'm not sure, but yeah.
As to the other data structures, I think when we start thinking about that, there will be a lot of data structures which would want to be mapped per domain, but not globally. At which point, so things like the shared info, and all vCPUs need access to that, but you should never need to go and look at the shared info from a different domain. In context, so I think a lot of data will split up on a per domain basis for reducing visibility, but then we get onto the per PCPU individual mappings for hiding the rest of the stuff that really should be segregated per vCPU, and that's where the complicated logic comes in.
Yeah, I agree. Like a lot of things, they probably don't need to be. I mean, globally mapped. There are different definitions of globally mapped. So, like, globally means the entire time, or just globally mapped in the per domain region. I mean, a lot of things, as you said, yes, I think they can be moved to the per domain region. So we hide them by virtue of switching the page table, but we still don't pay a much cost of mapping and unmapping them manually. Yeah.
Yeah, that would then get you into the area of having some kind of per domain memory allocation if you want to do that efficiently.
Okay, so yeah, I'm looking at the chat. Well, there's actually a lot of discussions. I don't know if.
So what sort of MMR emulation you're seeing?
It's HPAT emulation.
It's HPAT. But there's already also the PV time sources. Why not just get rid of HPAT altogether?
I think I can answer that with Windows.
Windows, yeah. Okay.
Yes,
exactly. I see.
Yeah, what we found is that I think Windows is now mostly it's using the TSC, but in some of the cases it's still using the HPAT. Even though you have invariant TSC available to it, it will still use HPAT in some cases, especially in media applications. So, so that's why we still need to make HPAT fast. Yeah.
Okay, I see.
On the subject, so earlier you said one performance consideration was to start using the physical ABI. Unfortunately, that doesn't help you with MMIO emulation because all of that starts from virtual addresses in the registers. As for mapping the EPT, that is entirely fine because what happens in the processor is that when you switch into non-root mode, the processor will read the VMCS and the EPT tables into cache. So an attacker in HVM non-root mode can already read its own EPT tables, at which point there is no extra safety by having them unmapped in the hypervisor.
Okay, sorry.
No, go ahead.
I think the point is whether an attacker can read the EPT of other domains.
Right. So if it's a per domain mapping that you're using rather than a global mapping, then you've successfully isolated it. But it's perfectly fine to sit and live in the per domain mappings.
Okay. Yeah. So for now, basically, my implementation is still leave it globally mapped. It's not even in the per domain region. But if there is any concern that EPT can contain any sort of secrets, I think I can also explore a per domain mapping. So,
I guess it depends on what you consider secret in terms of physical memory layout. And of course, people can do interesting things with that. They can try and figure out where it's better to row hammer or not. But again, that's far easier to do within your own domain. And you can already do that anyway without ever taking a trap to the hypervisor. So I wouldn't say that that's necessarily massively interesting to protect against.
Thank you. Okay, any other questions? Yeah, who wants to run Windows? I don't want to run Windows, but for
so that was a joke. I was when Wei was asking about who needs a HPAT, and the answer is Windows. And the joke is like, well, because Wei works for Microsoft. So anyway.
Okay, I see there's still probably one potential question.
So one other issue that you spoke about was caching some of the EPT translations. Unfortunately, guests can change it all that they want. So in particular, they at the moment in the HVM ABI they have arbitrary control via the increase reservation, decrease reservation hypercalls. Now this is an aspect of PV guests that should never have made it into HVM to begin with, but they have. It's going to be something we're taking out in the new HVM ABI, but a consequence of that is why the Xen security supported number of vCPUs is currently 32, because if you have 64 of them taking contention on the P2M lock, you can cause problems. So there are concerns in that area which I'm planning to fix with a new ABI, because I can't see a reasonable way of fixing it given the current ABI.
Okay.
So it's definitely not the case that the EPT map is static.
So actually what I was thinking is if a guest still needs a hypercall, for example, needs some Xen intervention to change the EPT, we could just invalidate the cache or change the cache in that path. But of course,
yes, you can, but just don't presume that it is a rare occurrence.
Yeah.
It is under guest control.
Yeah, we have another question from Julian. Yeah, I think that's a good point. So basically, we need, unfortunately for now, EPT walking needs to be fast. So we relies on fast physical to virtual address conversion, and moving it to a per domain region. At least at the moment, we don't have a good mechanism to make sure that is fast. So I think that's a good point. But I mean, for other secrets which don't rely on fast page table walking or fast VA to PA conversion, those things can be moved to the per domain region, I think.
That's a reasonable concern. In practice, we can see about coming up with alternative schemes here. And the fact that our current conversion macros are a little bit terrible doesn't mean that we shouldn't see if we can improve them.
Okay. Yeah, I do apologize. We are running up to, well, we already exceeded the time limit. So that's it. Okay. Thank you very much. I also hang around in the hallway chat. Thank you.